Okay, so for this portion, we start with the alkanes. And alkanes are generally hydrocarbons lacking pi bonds. They are termed saturated because they have the maximum number of hydrogen atoms, and they are sp3 hybridized, meaning that they consist mostly of single bonded carbons. Okay, so alkanes use the suffix -ane, and here are some examples: methane, ethane, butane, cyclohexane, and bicycloheptane. Okay, so alkanes are typically named using a set of prefixes. And these prefixes, if you may notice, from number 5 onwards, they take on the prefixes of polygons: pentagon, hexagon, heptagon. And so attaching that to the suffix -ane will yield us our alkane name. Okay, pentane, hexane, heptane, octane. Notable are the first 4, which are not using the polygon names. Rather, they use a set of historical prefixes. And these prefixes are meth for 1 carbon, eth for 2 carbon, prop for 3 carbon, and but for 4 carbon. Okay, so these are the prefixes. Now, let's take a look at this alkane here. So this is a structural formula. Let's count the number of carbons that it contains: 1, 2, 3, 4, 5, and 6. Okay, so if it has 6 carbons, then it must use the prefix hex. Okay, so it is hexane. Okay, next, how about this one? Well, let's count the number of carbons. Okay, 1, 2, 3, and 4. So it has 4 carbons, and so it must use the prefix but. Okay, but. And so the name of our alkane is butane. Okay, let's try this one. Okay, so let's count the number of carbons based on the formula. Okay, we have 1 carbon here. We have another carbon here, so that's 2. And then we have a chain of carbons in the middle, which are equal to 20. Okay, so we add 20 and the 2, and we get 22 carbons. Okay, so we use 20. So the 20 portion of the prefix icos is actually the cos, while we add the 2 in the end using the ones with the tens. Okay, so we use do. Okay, so do cos, do cosine. Okay, so quite simple. Okay, now we go on to branched alkanes. Okay, and for branched alkanes, what you first want to do is look for the parent chain. What is the parent chain? It is the longest continuous chain of carbons. Okay, so from this, you can visualize, okay, which is the longest chain of carbon. If you cannot visualize it easily, you can try going at one corner and seeing if it goes through longer paths until you are able to trace the longest path. So it's this one. Okay, so that's the longest chain. Now we name it nonane. Why? Okay, let's count how many carbons it has. It has 1, 2, 3, 4, 5, 6, 7, 8, and 9. And if we go back, okay, we have 9 carbons, which means we use the prefix non. Okay, so it's nonane. Okay, so that's the parent name. Okay, now in determining the parent chain, make sure that you are able to consider all the possible parent chains. Okay, So sometimes you can find two equally lengthy parent chains, and so you may encounter a tie. Okay, and if there is a tie, what you want to do is choose the parent chain that will give the greatest number of simple substituents. Okay, so we want a larger set of simple substituents without any branching points compared to one big complex substituent. Okay, so we will elaborate complex substituents later. Okay, so proceeding from that, okay, we have the parent name. Now what we want to do is identify the substituents. Okay, so how do we do that? Okay, let's label all of these substituents. So we have these. Okay, we have these substituents. Okay, what you want to do is to count the number of carbons that are connected to the parent chain. Okay, so for example, this carbon is just a singular carbon that's connected to this parent chain. So we have a 1 carbon substituent, and so we will use 1 carbon meth. Okay, and then we will attach a suffix, okay, that denotes that it is a substituent. So we will use the suffix il, YL. Okay, so this carbon that has one carbon connected to the parent chain, we will use methyl. Okay, the other one has 2 carbons connected to the parent chain. Okay, 2 carbons branching out, and we use the word ethyl. Okay, there we go. And for this one, it's the same, 1 carbon connected to the parent chain, methyl. Okay, 1 and 2. Okay. Okay, so now we have the name of the substituents and the parent name. We now begin locant numbering. Okay, in this case, what we do is we number the carbons of the parent chain, okay, in a specific direction, okay, in order to give the substituents their corresponding positions. Okay, because we cannot just leave it like that. No, we have to add numbers so that we won't have isomers that have different structures. Okay, so we have a specific name containing the locant number. Okay, so what we first do, we can draw both directions actually. So we can start from the right, the green path, 1 to 9, and we can start from the left, 1 to 9 as well. Okay, and now what we want to do is to choose the direction that gives the lowest number to a substituent. Okay, so here are the numbers that we have. Let's arrange that. Okay, if we look at these two, 4 and 3, these are the lowest numbers for each of the directions. Now, the green path has 3 as its lowest number, while the blue path has 4 as its lowest number. And so, we will choose the green path because it has the smaller number among its set. Okay? So it's the green path that we will choose. And after that, what we can do is arrange it. Okay? So we assign the substituents to their corresponding numbers, and we will now start to assemble the name. Okay? So what we want to do is we group the identical substituents and prefixes with a multiplicative prefix. Okay. So what are the multiplicative prefixes? We have for two multiples we use di, for 3 multiples tri, tetra for 4. Okay, and then continuing on to the polygon prefixes. Okay, and then we arrange the substituents in alphabetical order. Okay, so which comes first? E before M. Okay, and note we have to disregard multiplicative prefixes. Okay, so the di, if we attach di here, dimethyl, we will not consider that in the alphabetization, but there are exceptions which will be discussed later. Okay, after that we arrange the locant numbers in ascending order. Okay, so if we have to combine these two methyls into a dimethyl, we arrange their numbers in ascending order. So 3, 6. Okay, 3, 6 dimethyl. Okay, there we go. And so this is how we assemble the name. Okay, once the multiplicative prefix is added, we've arranged the numbers. We then connect the names together by using commas and hyphens. Okay, we use hyphens to separate numbers from letters. Okay, and we separate numbers between each other using commas. So the final name of this compound is 4-ethyl 3,6-dimethyl nonane. Okay. Okay. Now, here are some tie cases in locant numbering. So you may encounter these, and this is how to solve them if you encounter a tie. Now, if there is a tie, let's say for example this one, we have two directions, and we should look at the smallest number on each direction, and as you can see they are 2. Okay, they are both 2. So when we compare them together, we cannot reach a decision. No? So what we have to do, okay, is look at the whole set. Okay, we can look at 2, 3, and 5, 2, 4, and 5. Okay. So what we want to do is we want to look for the set that gives low numbers to more substituents. Okay. So these two number 2s, they're the same, so we can't really compare them together. Okay. But the 3 and 4, we can compare those two. 3 is lower than 4, and so 2, 3, 5, or the green direction, would be the one we will choose. Okay? Okay. 2, 3, and 5. Okay? But how about if there is still a tie? Okay? Take a look at this. We have two substituents, 3 and 4 on the green direction, and 3 and 4 on the blue direction. They are the same. Okay, so how are we supposed to make a decision? Okay, so what we can do is we can look at the substituent names. As you can see, this one is a methyl and this one is an ethyl. Okay, and look at the alphabetization between those two substituents. So you have ethyl and methyl. Ethyl beats methyl because it comes first alphabetically, and so we will use the green direction. Okay, so 3 and 4. Okay, let's try these exercises. Provide the systematic name based on the structure. Okay, so what we can do is we can first determine the parent chain. Okay, so we have 1, 2, 3, 4, 5, and 6. Okay, 1, 2, 3, 4, 5, 6. So this is a hexane. Okay, hexane. And now what we want to do is determine the substituents. So we have this one. This is a methyl, 1 carbon. This one, methyl as well, 1 carbon. Okay, and so we have 2 methyls. We can combine that to make a what we call a dimethyl. Okay, so if you add these two together, we get a dimethyl because they are the same and they lie on the same parent chain. Okay, now what we want to do next is numbering. Now here's a shortcut. You don't have to write both of the directions, but in some complex cases you may want to write the directions. But in this case, I will look at it visually, and I will see where can I start on this parent chain that will give me lower numbers for my substituents. I think this one, if I start from the right, now I can get a smaller number set. So I will start here. I'll start with number 1, number 2, number 3, number 4, and number 5, and number 6. Okay? And what we will be using in the name is just the ones that have substituents. Okay? So when we finally assemble the name, okay, 2, 4, separate the numbers with a comma. Dimethyl, so that's our group of methyls. So we have 2-methyl, dimethyl. And then our parent name. Don't attach any spaces between them. Just continue the word hexane. Okay. This PowerPoint comes with the answer, so we can check if it's correct. Okay. 2,4-dimethyl hexane. Okay. Let's try another one. Okay. Let's count. 1, 2, 3, 4. I think this will go in a longer direction. 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Okay. So we have 7 carbons. And so we will use the prefix hept from heptagon, heptane. Okay. And then we will attach our group substituent. 1 carbon, methyl. Okay. Then we can do the numbering. Okay. Well, it seems to me, visually speaking, you can try to confirm this, but any direction we approach it, we will still get the same number. Okay, so I'll start from here. 1, 2, 3, 4, 5, 6, and 7. Okay, so this will be 4. So we have 4, position 4, we have methyl, and we have heptane. Okay, 4-methyl heptane, let's confirm that. Yes, okay, that's correct. Okay, and let's do this number 3. It's arranged weirdly, but you should be able to find the longest chain. You can try looking at it from here first. 1, 2, 3, 4, 5, 6, and 7. 1, 2, 3, 4, 5, 6, 7. Okay, so we have 7, so we have another heptane. Okay. And we have our substituents. Okay, let's count. 1. We have another methyl. 1 carbon, methyl. Okay, methyl. Okay, methyl. Okay, so we have 4 methyls. Okay, so we can actually combine all those together. They're all connected to the same parent chain, and so we can name it. If we add all of these together, we can name it tetra. Okay, for 4 methyl. Okay, You have tetramethyl, that's for 4 methyl groups. And now what we want to do is do our numbering. Okay, and it seems that if I start from this left-hand direction, I will be getting smaller numbers for our substituents. So I'll start here. 1, 2, 3, 4, 5, and 6, and 7. Okay, so you have 2, 3, and 5. If I started here, I would have gotten 1, 2, 3, 5, 6. So that would be too high. So you have to start with start from the left direction. Okay, and so combine those 2. Okay, now we have 2 methyls in the same position. Okay, so what we want to do to the locant number is we want to repeat it. Okay, so repeating it emphasizes that in that position number 2, there are 2 substituents of the same kind. Okay, so we'll repeat the number 2. 2, 2. We have one at 3. We have another one at 5. 2, 2, 3, 5. Tetramethyl. Okay, then our parent name, heptane. Okay, so let's confirm that. 2, 2, 3, 5 tetramethyl heptane. Okay, so that's for our branched alkane. Okay, so again, for 2 identical substituents in the same position, repeat the number in the systematic name. Okay, so here's just an additional point regarding common naming. So sometimes in the laboratory, we won't be able to encounter systematic names, but rather have to deal with common names. Okay, so a quick Google search should tell you what exactly is contained in these bottles that have a common name on them. But here are some general rules on how people name straight chain alkanes and branched alkanes in a common setting. So for example, straight chain alkane reagents normally come in a label containing the N prefix to denote that they are straight chain alkanes. Okay, so N-pentane can be another name for plain straight chain pentane. N-hexane for hexane. Okay, and this applies for alkanes with 4+ carbons because 3 and below carbon alkanes are always straight chain. Okay, so that's for straight chain alkanes. Branched alkanes sometimes can have the iso prefix. Okay, and that iso prefix is this a propane group attached to the end of a certain hydrocarbon. So for example, isobutane, this is its structure. It's a 4-carbon alkane, branched alkane. Isoheptane containing this iso group as well. Okay, sometimes it can also have the term neo. Okay, and that neo group has a isobutane group at the end of a carbon chain, so it has a quaternary carbon right in between. This is neopentane, that's 5-carbon neo group. So as you can see, you can also you'll also notice that in common names there is no parent. The parent names are usually interchanged, no? So interchanged in such a way that they don't count the longest chain but count the total number of carbons. So this is a pentane, no, but there's not really a pentane parent chain. Okay, same thing here with neoheptane, that's 7 carbons in total. Okay. Okay, so always take common names with a grain of salt, no? So you really won't be able to find a distinct pattern if you go on to higher weights of uh, alkanes, for example, when you look at their common names. For example, isooctane. Isooctane would might look like a long chain 1, 2, 3, 4, 5, 6, 7, 8. It may look like that, but actually, what's being sold in reagents looks more like this. So it has an iso group and a neo group, and that is what is conventionally termed as isooctane. Okay, so it really doesn't follow a discrete pattern. Okay. Okay. So now we go on to our alkane complex substituents. Okay. So we'll be using the 1993 convention because that's the typically used convention in board exams in the Philippines, as well as common textbooks that have not yet been updated. Okay, so what we encounter here is a substituent that has its own substituents. So it's like substituentception. Okay, so let's take a look at this one. Okay, so I've already labeled the parent chain. We have undecane. Okay, so that's 11 carbons. And we have a complex substituent right there. Okay, so what we want to do first is to count the number of carbons from the connection to the parent chain. Okay, so from the connection, what do I mean by that? What I mean is the carbon starting from the carbon here, okay, this carbon, that connects to the parent chain. Okay, and so we have to look for the longest chain from that carbon. Okay, and so let's try counting that. We have 1, 2, 3, and 4. So that's 4 carbons. Okay, again, I just labeled the number Locant number. So we have 1, 2, 3, 4 carbons, and so we have a butyl group. Okay, so that's our substituent parent. Okay, so that's the substituent parent name. We have a butyl group there. Okay, and at position 2, okay, we have a methyl group. Okay, so there's our compound name. Okay, so after that we have our locant number, our substituent locant number, that's number 2. We have a methyl there, and then we have a butyl group. Okay, and so what we do is we assemble the complex substituent name. Okay, and what we do is we enclose that whole group, okay, in what we call the parentheses. Okay, so we have a parentheses that separates the whole substituent group from other substituent groups, for example. Okay, so this whole portion is 2-methylbutyl. Okay, so we enclose it there. Okay, it's important to note that the Greek prefixes inside this group, if we have multiplicative prefixes like di, tri, etc., they are now considered in the alphabetic order of our complex substituents. Okay, so if we have a di inside, dimethylbutyl, for example, we have to consider it in the alphabetization now. Okay, and so let's try assembling the name. Okay, so we have number 6 as our Locant number in the parent chain, and so we simply attach it like so. Okay, so the final name is 6,2-methylbutyl undecane. Okay, there we go. Okay, now let's encounter a situation where we have 2 complex substituents, okay, that are identical. Okay, so here we have tridecane, so that's 13 carbons, and we have two identical complex substituents, okay, at position 6 and 7, okay, one methyl butyl on one side and the same on the other. Okay, so how do we combine these two since they are identical? Well, we use the prefixes bis, tris, and tetrakis. Okay, and this goes on further, pentakis, hexakis. Okay, and that will denote how many of these multiple complex substituents we have. Okay, so if we try assembling the name, we have 6, 7. We have two of those 1-methyl-butyl groups, so we use bis. Then we have 1-methyl-butyl, that's the name of the complex substituent, and then tridecane. Okay, so here are some more prefixes. Okay. Okay. Now, IUPAC, the original, the source where we get the systematic naming rules, also recognizes these complex substituents as valid for systematic names. Okay, so if you do use these in systematic names, as long as you use them properly, they are valid systematic names. Okay. However, these can only be used without substitution. Okay, so if you have an isopropyl group, for example, you cannot attach anything to it and change its name to, for example, 2-methyl isopropyl. You cannot do that. You can only use isopropyl if it's that exact group. Okay, so no substitution. You cannot add any substituents to it. Okay, so some of these are isopropyl and tert-butyl. These are the most common, actually, these two. So you can memorize that, how they look, and use them to simplify your naming. Here are some other ones, less common, such as isopentyl, tert-pentyl, sec-butyl, isobutyl, and neopentyl. Okay. So again, what does it mean when it cannot be substituted? It means that if I attach any group to it, it won't be a valid name anymore. Okay, so for example, if I have isopropyl and I attach a chlorine group and then I add chloro to it, not valid. Okay, what is valid is if I use its actual systematic name, not just the accepted one. 1-methyl ethyl, I attach 2-chloro to the 1-methyl ethyl. That's a valid systematic name. Okay, so isopropyl cannot be substituted because it is distinct. Okay. Okay, so let's try these systematic name based on the structure. So this is a simple, easy exercises. Okay, so let's try. Okay, let's count the number of carbons in the longest chain. 1, 2, 3, 4, 5, 6, 7. So we have heptane. Okay, and then we have our complex substituent. Okay, so let's try first our you may be able to recognize that this is isopropyl, but let's try doing the proper systematic naming first. Okay, so what we do is we start from this carbon, that's 1, and then we go and find the longest substituent parent chain, 1, 2. So we have 2 carbons here, and so this is ethyl. Okay, and at the 1 position of that ethyl, we have a methyl group. Okay, And for our heptane, it's equidistant from both sides, so I will start here 1, 2, 3, 4, 5, 6, and 7. Okay, so it's number 4. Okay, so let's first assemble the substituent name in parentheses. Again, it will cause confusion if we don't put it in parentheses, so place it in parentheses. We have a 1 at the 1 position, we have methyl, and then it's attached to an ethyl group. Okay, 1 methyl ethyl. That 1 methyl ethyl is at the 4 position of our parent chain. So 4 parenthesis 1 methyl ethyl. Okay, heptane. Okay, so let's confirm. Okay, so one of our answers are accepted. Okay, so that's for 1 methyl ethyl heptane. Or you could have written it in the shortcut accepted by IUPAC for isopropyl. So this is an isopropyl group, heptane. So that's also valid. Okay, this grayed out one, you don't need to mind it, but it's actually the 2013 updated version. So if you were to, for example, go abroad and someone says, oh, can you hand me the 4-propan-2-yl heptane, you may be able to at least get a grasp of how it's being named, but we will focus on the 1994 method for the time being. Okay. So let's look at the next example. Let's look at the longest chain. 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have 9 non-ane. Okay. At position 1, 2, 3, 4, 5, we have a complex substituent. At the connecting carbon, we will count 1, 2, 3. So that's the longest chain we can make. I could have went upwards, doesn't matter, as long as we find the longest chain of carbons. Okay, 1, 2, 3. So that's 3, and so we have a propyl group. Okay, and then at these 2 positions, okay, so what are those 2 positions? 1 and 2. Okay, we have methyl and we have another methyl. Okay, so we have 2 methyls at 2 different positions, and so when we write the complex substituent name, we will write it like this. Okay, parentheses 1, 2 dimethyl. Again, we have 2 methyl groups, propyl. Okay, 1, 2 dimethyl propyl. So that's our whole complex substituent name. I will do the numbering: 1, 2, 3, 4, and 5. So at position 5, okay, at position 5, we have 1, 2 dimethyl propyl. Okay, non-ane. Okay, so there we go. 5, 1, 2 dimethyl propyl non-ane. Okay, let's go on to the last easy example. Let's do this. Longest chain, 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so we have nonane again. Okay. And we have 3 of these, okay, groups, and they actually look the same. But let's confirm that. So I will do again 1, 2, you have 2 ethyl. This one 1, 2 ethyl. 1, 2 ethyl. And at positions 1 of each of them, actually, they have a methyl group. Okay, methyl. Okay, so they all have the same general complex substituent name of 1-methyl ethyl. Okay. Okay. And if we do the numbering, okay, I will try to start from here. 1, 2, 3, 4, 5, 6. So 4, 5, and 6. If I start here, 1, 2, 3, 4, 5, and 6. So it doesn't matter. I can start from any other direction, as they are all identical. Okay. So at position 4, okay, 5, and 6, I have 3. Okay, I have 3 of these complex substituents. So remember, if we have 3 complex substituents that are identical, we have to use the bis tris tetrachis. In this case, we have 3, so we will use tris. Okay, and then we will add our name, 1-methyl ethyl, and then nonane. Let's see if that's the same. 4, 5, 6, tris, 1-methyl ethyl nonane. Okay, and we could have gotten a shorter name if we used isopropyl. I should probably highlight this. If we use the isopropyl name, okay, or any other accepted short form for a complex substituent, okay, we will not be using tris anymore. We will be using tri. Okay, so that's the same for the regular substituents. Okay, so we treat isopropyl like a regular substituent. We use di, tri, tetra. Okay, but for a parenthesis separated complex substituent, we have to use tris, bis, tetrachis. Okay. Okay. So let's try doing this moderate example because there's something that must be emphasized. Okay. So here's the answer, but I have to emphasize something here. So we have a situation that I've mentioned in the earlier slides, that we have 2 choices for the parent chain, okay, and both have an equal distance, but one gives, okay, I will show this in blue. One situation gives 2 small simple substituents, while the other gives 1 large complex substituent. Okay? If you have a choice between those 2, choose the one that will give more simple substituents. Okay, so we choose the path which gives more simple substituents. Okay, so if for example you're strolling along looking at the longest chain, okay, it seems that if we branch out this way it'll be too short, this way it'll be longer, so we'll go this way. We stop here and we encounter a junction which is equidistant. If we approach it towards the simpler chain, we will get a large complex substituent. But if we approach it through the direction which has a substituent, we will be left with two simple substituents. And so we want to maximize the number of simple substituents. Okay, so we have two simple substituents, and then we can continue naming. Okay, and if you will confirm the name, you'll be able to get 1, 2, 3. At position 3 we have methyl. At position 5 we have butyl. So these are the two simple substituents. 6, 7. At position 7 we have 1, 3 dimethyl butyl. 1, 2, 3, 4. So this is the butyl, and these are the two methyl groups. Okay, and we have our 12 carbon dodecane. Okay, error here, there shouldn't be a hyphen. Okay, so that's for complex substituents. Okay, so we've been dealing with straight chain alkanes and branched alkanes. Now we go to our cycloalkanes. Okay, so alkanes that form rings within each other, and so they form these simple polygons. Okay, so they are named like polygons, and so what we do is we add a prefix cyclo, okay, to denote that it is in a cyclic form to the parent name. So for example, a simple triangle has 3 vertices, and so each vertex is a carbon, and so we have 3 carbon propane. You attach the prefix cyclo, cyclopropane, okay, followed by cyclobutane, 4 carbon, cyclopentane, and cyclohexane. Okay, so let's say we have a substituted cycloalkane. So what we first do is we identify the parent chain. So the parent chain would be our cyclic alkane. Okay, that's our cyclopentane. Okay, after that we identify the substituents. You can see we have a methyl and an ethyl group. Okay, and then we proceed to locant numbering. Now, why did I number it this way? Well, an alkane, a cycloalkane, is generally like a straight chain alkane, but you can start the numbering anywhere. Okay, because every part of the cycloalkane is not an edge, no, so it's just a point within the alkane itself. So I can start it anywhere. So the problem with that is that where do you start? Okay, and so in this case we have to start based on our third tie criteria, where we have to look at the alphabetization of our substituents. Okay, so E comes before M, and so ethyl before methyl. Okay, so that's why I placed 1 at the ethyl group and 2 at the methyl group. After that, we assemble the name like so: 1 ethyl, 2 methyl, cyclopentane. Okay, simple. Okay, So we name them like alkanes by identifying the parent chain. Okay. And in much the same as all names, there are some rules with regards to choosing the parent name. Okay. In this case, cyclopropane has a higher priority over the straight chain alkane regardless of the length. Okay. Rings are preferred over straight chain alkanes. Okay. But again, if you decided to write the straight chain alkane as the parent chain, okay, it's still an acceptable systematic name, but it is not the official IUPAC name. Okay, so if you want to stick to the official IUPAC name, IUPAC systematic name, rings should be preferred. Okay, so that's the preferred IUPAC name. Okay, now if for example you have a parent chain that has a cycloalkane substituent, okay, what you do is you approach it this way. Okay, you first name the cycloalkane substituent like so. We have a 3-carbon cycloalkane, cyclopropyl. Okay, and then at position 2, 1, 2, 3, okay, at position 2, again we set 1 as the point which the parent is connected to the substituent. 1, 2, at position 2 we have a methyl group. Okay, and so our substituent, this is a complex substituent, is 2-methyl cyclopropyl enclosed in parentheses. Okay, so that's for our cycloalkane substituents. Okay, so at this point we've encountered so many complex substituents that we now have to look at alphabetization and when to consider it and when not to consider it. Okay? Okay, so recall that multiplicative prefixes are disregarded in alphabetization. So do not consider our tetra, di, and bis when alphabetizing our complex substituents and simple substituents. However, if it is enclosed in a parenthesis and it is a complex substituent that has a inner substituent that has a multiplicative prefix, we consider that. Okay, so enclosed in parenthesis the first letter. Okay, the prefixes tert and sec are disregarded in alphabetization. Okay, I guess a simple clue to this is if there's a dash in the accepted substituent, and if it's in, if it is a dash and it is in italics, okay, like sec-butyl, tert-butyl, you should disregard that prefix for alphabetization. Okay, likewise, or conversely, iso and neo, since they are part of the complete complex substituent accepted name, they are considered in alphabetization. So you consider the I and N in isobutyl and neopentyl. And the prefix cyclo, okay, for cycloalkanes, that is also considered for alphabetization. Okay. Okay, so let's try these two simple exercises for cycloalkanes. Okay, so we have red here for our parent name. Okay, so let's look at the ring So rings are preferred over alkanes. We have a 6-membered ring, 1, 2, 3, 4, 5, 6. So this is a cyclohexane. Okay, and before we start numbering, let's try to identify each substituent first. We have here a methyl group, starts in M, and then we have a ethyl group with a methyl inner substituent at the 1 position. At the 1 position. Okay. So this is a complex substituent of the name 1-methyl ethyl. Okay. So how do we alphabetize it if we have methyl and methyl ethyl? Okay. So remember, in a dictionary, if we have a root word, or not a root word, for example, butter and butterfly, butter always comes before butterfly in the dictionary. So nothing followed by something. Okay. So butter will come first, and so methyl should come first as well, because in the alphabetic order, if we have a word following methyl, that should come after. Okay, so we'll give the numbering 1 to methyl, followed by 2 and 3. Okay, so we have a 1-methyl, okay, 3 parentheses 1-methyl ethyl, cyclohexane. Okay, so again, 1-methyl, 3 1-methyl ethyl, cyclohexane. Okay. Okay, so again, methyl comes before methyl ethyl in the alphabetic order. Okay, so if we had the situation where we use isopropyl, okay, instead of 1-methyl ethyl, then that numbering will be reversed. Okay, so it matters if you use the shortcut or if you use the regular method. Okay. Okay. Let's try the next one. We have 1, 2, 3, 4, 5, 6, 7. Okay. 1, 2, 3, 4, 5, 6, 7. So we have a cycloheptane. Okay. Let's look at each substituent. We have a methyl group. We have a ethyl group. We have a 1, 2, 3, 4 butyl group. At position 2, it has a methyl inner substituent. Okay, so this total complex substituent is 2-methyl butyl. Okay, so let's try arranging it in order. Okay, E comes before M, so we'll get We'll set it as 1. Okay, and now we have to go in a direction that will give us a lower number for all substituents regardless of their alphabetization. Okay, so we have to proceed 1, 2, 3, 1, 3, 4, and 5. So 1, 3, and 5. If we went the other way, I would have gotten 1, 4, and 6. So the green direction should be followed. And so when we assemble the name, we should be able to get 1 ethyl, 3 methyl, and 5, okay, 2 methyl butyl, cycloheptane. Okay, let's see. Okay, 1 ethyl, 3 methyl, 2 methyl butyl, cycloheptane. Okay, so I did highlight it to highlight the difference in alphabetization, but in this case it doesn't matter. What matters is we numbered it in such a way that they will have lower numbers. The choice, however, ethyl being the first, okay, is because of its alphabetization. Okay. Okay, so now we go on to bicyclic alkanes. Okay, slightly more complex, but it should be quite simple. Okay, so we start with bicyclic alkanes, which are 2 rings, okay, that are separated by a common carbon, okay, or a bond. Okay, so these 2 rings are connected by bridgeheads, and they are carbons which have 3 connections, okay, each linking the 2 rings together. So these are the 2 bridgeheads. There are 2 ways to draw bicyclic alkanes. One being a flat form, looking from the top, for example, like this one, or you may draw it in a 3D perspective, like this one. Okay, either case is acceptable. In some cases where you have stereochemistry, okay, you may have to choose between one of them to best express the structure you want. Okay, and so when naming these, we consider the total number of carbons. So in this case we have 1, 2, 3, 4, 5, 6, 7, 1 in the middle here, heptane, and then we attach a prefix bicyclo to denote that it has 2 rings. Okay, so this is a bicyclo compound. Now we have this weird set of numbers. I'll explain how these work in determining the structure. Okay. Okay. So what we first want to do is look for the parent chain, and this will be the bicyclic compound itself. And what we want to do is count the total number of carbons in the bicyclic ring system. Okay, so if you have any straggling substituents, do not count them. Only count the total number of carbons in the ring system. Okay, so this is a heptane as we determined in the previous slide. Okay, and what we want to do next is identify the bridgeheads which link these 2 rings together. Here are the 2 bridgeheads. Okay, following that, okay, from the bridgeheads, you can see I've color-coded them. There are 3 paths. Okay, there are 3 paths. What you want to do is count the number of carbons in each path. Okay, so and how do we do that? Okay, so we count the number of carbons. From the bridgehead, we don't count that number. We count 1 here, and we have 2 here. The green path, we have only 1 carbon here. And the blue path, we have 2 carbons here. 1 and 2. Okay. And so we write the number of how many carbons are in each path here. 1, 2, 2. Okay. Okay. Then we assemble the parent name by adding bicyclo, a square bracket, the numbers in descending order. Okay. The numbers in descending order, so they should go down. 2, 2, 1. Okay. Separated by full stop or period, and enclosed in square brackets again. So bicyclo, square bracket, 2, full stop, 2, full stop, 1, square bracket, heptane, total number of carbons. And so that's how you name a bicyclic alkane. Okay? So quite simple. Okay. Now, what if we have a substituent? So I'll add a methyl group right here. Okay. What you first want to do is start at a bridgehead. Okay. For example, we have 2 bridgeheads here. We have this one and this one. What we want to do is start at a bridgehead that is closest to our substituent. Okay, so in this case, we start here, okay, this one, because it's closer to our methyl substituent. Okay. Then what we do is we number from the largest to the smallest path. Okay. Always in bicyclic alkanes, largest to the smallest path. Start 1 there, followed by 2, 3, 4. Okay. So we have 2 paths to choose from. Actually, we have the path with 2 carbons here and path with 2 carbons containing the substituent. We start going towards the direction with our substituent. So we have methyl there. 1, 2, 3, 4, followed by 5, 6, because that is our next largest path, followed by 7 at the very top. Okay. And so again, we choose the bridgehead that will satisfy the numbering rules, so it has to have the lowest number. So this is the configuration of numbering that will give us the lowest number for methyl, which is number 2. And so when we assemble the name, we have 2-methyl bicyclo 2,2,1 heptane. Okay. Okay. So here are some simple exercises. Provide the systematic name based on the structure. Okay. So let's try this. Let's count the number of carbons. 1, 2, 3, 4, 5, 6, 7. Okay. So this is a heptane. Okay. We have the bridgeheads here. Let's count the number of carbons in each path. In this path, we have 2 carbons. On this path, we have 2 carbons as well. And on this path, we have 1 carbon. Okay. So when we assemble this name, bicyclo, square bracket, the largest number, 2, full stop, 2, full stop, 1, and close, heptane, no spaces. Okay. Bicyclo 2,2,1 heptane. Okay. Let's go to the next one. Let's count the number of carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay. So this is an undecane. 1 dec meaning 10, So 11 in total on the cane. Okay. And then let's look at the number of carbons in each path. Let's determine the bridgeheads first. These are the bridgeheads. One, two, three, ayan. 1, 2, 3, 3. 1, 2, 3. So we also have 3 here. And 1, 2, and 3. 3 as well. So when you write the name, Bicyclo, 3, 3, 3, Undecane. Okay, let's see. Bicyclo 3, 3, 3, Undecane. Okay. Okay. Now let's look at this last one. Okay. Count the number of carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9. Nonane. Okay, so we have 9 nonane. And then let's determine the bridgeheads. These are the 2 bridgeheads. Okay, let's count the number of carbons in each path. 1, 2, 3, and 4. One, 2, 3. So I have 3 here. And what about this middle one? There are no carbons. So let's write 0. Okay. Now we write the name Bicyclo, square parentheses, largest number first, 4, followed by 3, followed by 0, nonane. Okay. Bicyclo 430 nonane. There you go. Okay. So there are some trivial names like this one. These are special IUPAC names, but you can also name it in the bicyclic system. Sometimes some bicyclic systems will show stereoisomerism, and so you may find some names to have stereoisomer prefixes. Okay, but that's for a simple bicyclic compound. Let's try some of these moderate exercises with the substituents. Okay, so it's quite simple. We can start first by counting the carbons in each in the whole parent bicyclic system. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so that is 10 decane. Okay, so let's count the number of carbons in each path. Okay, I will use one color. 1, 2, 3. So we have 3 in this path. Again, these are our bridgeheads. 1, 2, 3, 3 as well, and then 1, 2. You have 2 here. Okay. Okay. So when we start numbering, okay, but let's write our parent name first. Bicyclo 3, 3, 2, decane. Okay. Okay. And then we'll try numbering. Okay? So when we number, we want to start with the largest paths first before going to our smaller path. Okay? So we start here. Actually, we can choose any because our substituent is at the smallest path, which is the path with 2 carbons. So we'll just exhaust all our numbers. 1, 2, 3, 4, 5, 6, 7, 8, and then we can go up 9 and then 10. Okay? So at position 9, we have 2 methyl groups. Methyl. Okay? So at that position, at position 9, okay, at position 9, we have 2 methyl dimethyl. Okay, we forgot something. Since there are 2 methyls at the same position, we should repeat the number 9. Okay? 9,9-dimethyl. Then we continue the name, bicyclo. 3,3,2-decane. Okay. There we go. It's obscured, but it says there 9,9-dimethyl bicyclo 3,3,2-decane. Okay. Now, let's go to the next one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we have undecane. Okay. Bridgeheads. 1, 2, 3, 4. So we have 4 here. 1, 2, 3. 3 here. 1, 2. We have 2 here. Okay. So our parent name is bicyclo. 4, 3, 2. Undecane. Okay. And then it is followed by our substituents. So let's first name our substituents before anything. We have an ethyl group here, we have a methyl group here, and we have a methyl group here. Okay, and then let's do the numbering. We start at a bridgehead. We can choose between these two, but we always have to proceed through the path with 4 carbons in it. So we have to start in either of these positions. I will choose this one because it is closer to our 2 substituents here. Okay, so we will start here. 1, 2, 3. So we give them a locant number of 3, 4, 5, 6. Okay, and then we rotate. We continue through the next smaller path, number 3, 7, 8. So this one gets an 8, 9. Then we go up 10, 11. Okay, so we have 3 and 8. Okay, now we write the name. At position 3, we have an ethyl group. Okay, it comes before methyl because alphabetization. At that same position, position 3, we have a methyl group. Okay, followed by, at position 8, another methyl group. Oh wait, we forgot something. We can actually combine these two since they are both methyl groups. 3, 8 dimethyl, and we won't consider the letter D in our alphabetization, E and M, okay, followed by bicyclo. So we have no more space, so I'll put it down here. 4, 3, 2 undecane. Okay, let's see if that's correct. Okay, it's just obscured, but it says 3-ethyl 3,8-dimethyl bicyclo 4,3,2 undecane. Okay, and let's try our last one. Okay, let's count the total number of carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Decane. Let's count. 1, bridgeheads first. 1, 2, 1, 2, 3. 3 carbons here. 1, 2, 3, 4. Okay, so we have 4 carbons here. 1. Okay, just 1. Okay, and then we have 2 substituents that are cyclic, so we should use our cyclohexyl, cyclopropyl names. In this case we have 3 carbons, so it's propyl, and because it's a cyclic compound, cyclo. Okay, while this one, 1, 2, 3, 4, 5 carbon, pentagon, pent, til, cyclo, cyclopentyl. Okay, now let's do the numbering. We start with our bridgehead number 1. Okay, then we proceed towards the larger path. I started here because this is closer to our cyclopropyl substituent. 1, 2, 3. Okay, so we give it 3, 4, 5, and 6. Okay, then we proceed to the second largest one, 7, 8. So we give it 8, 9, and then 10 at the middle. Okay, then we form our name. Okay, so we'll arrange it. Okay, we'll start with 8 cyclopentyl. Why? Because we have E before R. Okay, cyclopentyl, 3 cyclopropyl. Okay, and then followed by bicyclo, 4, 3, 1 decane. Let's confirm that if it's correct. 8 cyclopentyl, 3 cyclopropyl, bicyclo, 4, 3, 1 decane. Okay, so that's for some substituted bicyclic alkanes.